much for being here and for accepting me. So I have called this learning between digital twins. What is a digital twin? There are many interpretations of that, and yeah, we'll come a little bit to our. So why am I here? I'm from the uncertainty side of things, but for the last year I've been involved in this project, the digital twin for essential hypertension management and treatment, which we call my MDT. So I'm a statistician. Uncertainty quantification is my home, and I'm now learning about cardiac modeling. It's a lot of new words for me. So the outline of this talk, I start a bit explaining the aim of our project. We are quite ambitious. Then my experience from uncertainty quantification, especially for predictions, when they are based on physical models, on mechanical understanding, if we want, mechanical models. I have done a bit of that for a complex system of the last 15 years, a lot of struggling. And then at the end I'll do this learning between digital twins. Maybe I've learned from all my struggle, going one step back and exploring this in a simpler setting. If we can learn between the twins here. So about this project. So the aim is to have a platform for tailored or personalized hypertension diagnostic, prognostic and treatment. So it should be a living digital model. It should be based on physiological simulation or mechanical understanding and machine learning or statistics. We should integrate population data and sensor data from the individuals. And we are here into like kind of affordable sensors that most people can have, or maybe have already. Should also develop these. And our big, what we hope in the future is to radically improve prevention and treatment of hypertension. So here is the team of PIs, if you want. We have an exercise psychologist. We have biomedical engineering. Leif Rune is here. Product development. So this is designing the sensor and making it more identifiable. I'm the statistician. We have actually a medical doctor that's very much into biobanks and genetics, and then we have machine learning more from the computer science point of view. Fortunately, we also have some PhDs and postdocs and master students doing all the hard work. Well, in August it was the team. This was the team. It's also increasing now, and they are also they are as transdisciplinary as we are. It's a very exciting place to be, and a lot of words we don't understand here too between each other, but we are working hard on this. So why do we want uncertainty in this project? Why was I included? I would say it's two reasons, how I see it. One thing is that we should provide uncertainty for the users. This is going to be what we see here. We have population-based, we have a medical digital prototype. Then we learn about the person from the individual data, and we get a personalized, like my medical digital twin, and this is going to be clinical decision support system. And it's lots of uncertainties here, so we like to be honest with ourselves, with the patients. The uncertainty should be quantified. It's also another reason to quantify uncertainty, and that's when we combine data sources, we should quantify the uncertainty to do this in a proper way, or in a consistent way, theoretically. So a bit about my background. The best thing about being a statistician is that you can play in everyone else's backyard, and I have done that. My horsepower on barn owl research is using statistical models. It's quantitative genetics there, but then you use the dependency between them and model that to to get to know about heritability or to account for heritability. That will come in later here. I use the same approach. We use the same approach. Then I've also been doing, from different perspective, a good bit of this quantifying uncertainty for forecasts, different forecasts. It's wind and precipitation, flood forecasting, also wind energy forecasting, and in many of these integrating the physical model, meteorological models, hydrological models, physically based models with statistical models. So this is what I'm doing. So what is a good probabilistic forecast if we think about it that way? I know we can think about the weather forecast because that's relatively easy to relate to. A deterministic forecast is one value. I would say that tomorrow the wind speed will be 9.5 meters per second, period. We know it's not true, but okay. Then a probabilistic forecast, then we give a probability density function instead. So we say, okay, it will be Gaussian mean 9.5 meters per second, standard deviation of 1 meter per second. And this is an example of a probabilistic forecast from the ECNWF, European Center for Mid-Range Weather Forecast in Reading. So it's 70-hour forecast, and it's for different days, and then the observation are these dots. But what is a good probabilistic forecast? Does it look like a good probabilistic forecast? No, it doesn't. It's it kind of says it's a 95% interval, but maybe 30% of the observation is within it. We don't like that. So as a statistician, I want this really to be calibrated. It should be statistical consistent. In the long run, 95% of the observation should be within the 95% prediction interval, 80% within the 80% prediction interval, and so forth. So as a statistician, it's relatively easy to obtain that, but we also want it to be sharp. We want to be certain and have the uncertainty right. That's what we're aiming for. So that's the concentration, or you can say the width of the predicted distribution. I think it's almost 15 years ago I got to learn about continuous rank probability score. That's a score that combines both of these. If you're doing prediction and quantifying uncertainty and you haven't heard about it, you should look it up. It's a good score. I don't go more into it here now. Well, has good properties. So how could we construct probabilistic forecast? We can do it pure statistically. On average, it works well. In extreme situation, it's hard. It's kind of this extrapolation is hard, interpolation is easy thing. Or we can do it more or less model-wise. We can do post-processing, building an error model around what the deterministic model gives us. Process-based, that can be model uncertainty in input and propagate through the model. We have seen a lot of that here. We can make the model stochastic or account for the uncertainty in the parameters if you want, and combine all of them somehow. Here is an example. This is with the wind forecast still. It's joint work with a previous master student and research at the Norwegian Met Office. This is maybe a pure. What we get from ACMWF is a sample forecast that's based on perturbation of input and some uncertainty in the initial state. It's not calibrated, so what we do is that we post-process. Here we give each ensemble number, it's 52 ensembles, a small weight like that we estimate, and then we get a new calibrated version here that has good properties. And this is kind of the formula. So problem solved? Sometimes, but definitely not always. Yesterday we learned that to be taken seriously you have to quantify your uncertainty, but after doing so you might still have a problem with being taken seriously. If your model says, oh, there is a probability of 5% getting more than 500 millimeter precipitation tomorrow, it's a bit hard to be taken seriously. That's a lot of rain, a bit unrealistic, much rain. So maybe not that good. Of course, as the nerdy statistician, I could say, oh, but in the long term, the model behaves well, so I'm happy. But maybe not that satisfaction. No. And when it comes to like health and cardiovascular system, this is kind of telling people that they will die, so you should be a bit careful. But are we ready for probabilistic forecast? Well, the Norwegian Met Office thinks we are when it comes to precipitation or weather forecast for long term, or more than, for Monday on, more than 4 days, or 4 days ahead and forward. So you can go in and look at it and they explain what it is. And you need to choose a location in Norway, I realize, but then you get this for any location. And they have good properties. They only give kind of 80% uncertainty, so they maybe avoid the most extreme ones, but they have worked on this, done a good job. Yeah, so why do we want to do this? Several reasons. We want to have this uncertainty for the decision support. Another reason is also that for some people we will have a lot of data, high quality data and clinical data and this sensor data. So if we have a medical digital prototype, we can learn a lot for those, but can we use that knowledge for kind of the new people, those who doesn't have much data? That's what we hope we can do. And the question we will go more into here. So this is what I present now. It's basically a part of the master thesis of my master student Hong Tan Lam. We have focused on to predict and quantify uncertainty, and it's based on Tony O'Hagan's work. That's part of what he presented yesterday. So that's by using calibration of computer models, and we extend that by merging it with, or merging it more with linear mixed models. So then we can, instead in their work, to have like one simple machine here with theta equal 0.65 and a equal 20. So now we don't only have one person here or one patient, we have plenty. We have here 100, and they are not the same. This could have been done in different ways, but what we have done, that we said, yeah, it's a bit different here in the true model. And here we have 100 gray lines. Our simulator or computer model, what we think is the true is this linear model that kind of corresponds to the red line. So what have we learned the last couple of days? We have learned or heard a lot that all models are wrong, but some are useful. That's from Box. Maybe some of the message from Tony O'Hagan yesterday is that we do better if we kind of accept that we are wrong and learn from our mistakes, our model's mistake. And then our question is now, can we also learn from other models' mistakes, other people's models' mistakes? And kind of what we also learned that interpolation, that we can often do, that's good. Extrapolation is hard. So then we think, we now have many machines, we have 100 machines. When can we learn from other machines' simulators? So what we have done here, we have the first 50 have relatively much data. These are the points we will try to, 3 and 8, we will try to do predictions for. Then we have 10 machines that only have 5 data in the very low end. So for them, this is extrapolation. Then we have 5 that this is still extrapolation, but not that much, and some other designs here. Okay. So what we hope now is that we should be able to learn mainly from these ones, especially when we predict here, and maybe like here, when we only have very few data. Maybe we can learn something about the discrepancy, about the model from these machines where we have a lot of data in a larger range. So this is the Kennedy and O'Hagan model. Now we have hundreds of these models. So we have a J in addition to the I. I is the observation number and J is the patient number or machine number. So we need to add some J's. Like one option is that you just fit this model with discrepancy to each machine independently. Then we don't learn, but that's kind of our baseline here. It should actually be a J on the axis too, but that's too much. But we want to learn. What can we do then? We can say that the theta is common between them, and also this parameter in the Gaussian process. So we said that some of, like the parameters are common. We tried that first, it didn't work that well, so we go on. With a model 2. Okay, this is the same as model 1. And then we add something. We add a new discrepancy term, which comes from another Gaussian process, and this discrepancy term is common for all the machines. So we say that we can, something we learn for all of them, something else we have to, is individual. So here everything is individual. Here we have individual discrepancy but common parameters. And here we both have a common and individual discrepancy and then common parameters. Now, as a statistician, I now want to make an ideal machine, and that's ideal in the way that it's sampled from the model I want to fit. It's kind of, if it doesn't work here, it will never work. So I have this ideal machine, and then we also have the simple machine. So the results. Now we want to, we try to predict here at x equals 3. This is our prediction. We have the individual models, they are blue. Then we have model 1, that's green. Model 2 is black, and the observations are red. And we have set the posterior mean of model 2 as to 0, just to get it balanced here, easier to visualize. We see for the first 50 machines where we have a lot of data and we are doing interpolation anyway, it's not much of a difference. It's a little bit, but not much. For the next 10 ones, where we only have this few data, low values, we're really doing extrapolation. The blue one is, so that's the single machines are going crazy. The 95% prediction interval is out of the figure. The model 1 is doing a bit better, and model 3 it seems to be on right track here. We can learn between them. I don't go like, and then it's different patterns for the other designs. But we can also look at this in other ways. Here is, so we have in each of these boxes, like this box is the 100, no, it's the 10 machines that are here. And then it's box plot of the length of this prediction interval. And we see that, yeah, here, much data, interpolation, nothing much to gain, a little bit, but for the interval, a lot to gain for this one when it's extrapolation, and then it's a bit to gain for the other ones. Here is also the kind of same story for mean square error, and also for the continuous rank probability score. So we are doing better, especially for these ones, but also for some of these other when we learn between them. CRPS is smaller is better. And then for the a bit harder case, still it's a simple machine, but harder than the ideal machine. What's the story here? It's still interpolation for x equals 3. It's kind of the same, a bit. Much data interpolation, not much to gain. Few data and extrapolation. Here it really is a difference. The green one is making a bit funny things, and the blue one is totally off. Probably due to the theta parameter. Here you see that the mean square error is also outside the plot. And these ones are a lot better. The length of the interval is a bit more messy, but they are generally decreasing for when we learn between the models with a common discrepancy. And with CRPS, it's also kind of the same patterns. Now we're trying to do extrapolation. So we are predicting here, up here. Now it's extrapolation for everyone. And as we can see, it's more kind of that 5% of the observation is within the 95% prediction interval than opposite. So we are struggling still, especially this discrepancy model without the common discrepancy, our model 1. Yeah, and the other results agree with that. So what is our take-home message from this, exploring this simple model? Yeah, we can learn a bit between digital twin, and that's especially when it's extrapolation without the other ones, places you haven't been yourself. That's these ones. But poor extrapolation, what's extrapolation for everyone, is still hard. Like our computer model, our simulator isn't good enough for that. And pure interpolation, when we are here, it's not much to gain. You can do it, but you have so much data that you don't need to learn from the other ones. So, there I say thank you.
Thank you. Are there any questions? Could I maybe just quickly ask, when you started off, you talked that it was very interdisciplinary, very kind of collaborative, and you had a clinician, a medical doctor on there.
Oh, he used to be. Yeah, he's not anymore.
Did you ever kind of gauge from him, and possibly this applies to lots of other people, so how they might feel about being given a probability of something to be used in their clinical decision making, as opposed to kind of a binary yes or no?
And I think that it's too many years since he has worked as a clinician, but so no, not from him, but it's relating to uncertainty is often hard. I've experienced from other collaborators.
So for the hypertension modelling that you're kind of doing, do you think, and is this the tension that all of us face, is that you could make a statistical model of a non-physically informed statistical model of your patient and just feed data into that, or you could have a more physically constrained, biologically motivated model that might make people like me more happy, but maybe less good at predicting.
What I think we are approaching it is having a physically inspired model. Yeah, that's I think is this really forgetting that's needed. But then we respect the discrepancy and the uncertainty and try to learn these things between patients, like learn from that we have many models.
I think from what I thought you said, using priors so we're always a problem when you're trying to look at the discrepancy. Any parameter set can have a discrepancy, and so you can always get something where we have a lot of discrepancy.
Yeah, and these models are not.
But then, have you ever thought about how you might go about building those priors, what your discrepancy might like, to make that a more identifiable problem?
you need to have kind of, because these are not identifiable models. That's how they are, and we also have a lot of uncertainty around here. So we need to have kind of some physical-based priors. Though the good thing when you have these models with these models, they are starting to be more identifiable, like especially this one. Here we have this term that's still not identifiable, but you can learn more between them. That's kind of learning about what the changes normally are, which enable you to say something about the uncertainty for those you have very little data on.
Any other quick questions?
So when you fit your model through, it does better, but you've got a lot more data to tie down the common discrepancy compared to the other discrepancy. How much is the gain simply from the fact you've got a lot more data, and how much is it the structure of the model?
You think about model 1 and model 2?
Yeah, so model 2, the phi term, you've got all the data is feeding into the phi term, so that you've got 1 over n helping all your variances go down. So you'd expect that to be a better predictor in some sense, because you've reduced the uncertainty on that common discrepancy compared to the what you might call a residual discrepancy.
Yeah, this kind. Yeah. Yeah. So, but still, it's this one that's not identifiable. But you can in the model. No. So I think the important part here is that, like, we have also have an ideal machine 1, and then fit model 1 and 2, and then of course you can look at the difference when you plot them. So the important part is that in the real world, kind of in the simple machine here, it is a discrepancy like this, and when we have this here, we learn about this discrepancy without uncertainty here, kind of with relatively little uncertainty, and that takes up much of the uncertainty you have. So it's critical in this learning that you have the common one, if it is a common term. If not, it doesn't matter.
Okay, well, if there's no other questions, we just thank all of our speakers.